Okay, well, let's wait a couple more minutes since I think because I clicked resume late, people are starting to join only now.
Got it.
Yeah. Oh, wait, why is Daniel still on the stage? Okay. All right, Daniel. Yeah, so I'll do the Q&A at the end, and I'll just select questions from the Q&A and show them on screen, and you can like answer them, and hopefully we can hit the 90-minute bar, and Sam Lindley will be very happy once we get to 90 minutes.
Yeah.
All right, I think it's getting pretty filled up. Hi, everyone. It is my great pleasure to welcome Don Side for the keynote for this year's ML workshop. Don is well known for FSharp, the design implementation of FSharp, but also the stewardship of the community at fsharp.org and creating really momentum and bringing functional programming to a community that normally would not be aware of functional programming. So I'm particularly excited that this year we're fulfilling the premise of the ML Family Workshop, which is to welcome members of the entire family. And now I will leave the floor to Don to tell us about the history of FSharp. I was looking at the Wikipedia page, and it's been, what, 16 years since the first version? Time flies, doesn't it?
Since version 0.1, I think that's about
Yeah.
that is about right. Yep.
All right, the floor is yours.
All right. Thank you very much, everyone, for coming along. And thank you, Jonathan, for the introduction and for the invitation. And just looking at who's here. Oh, we got Claudio. Hello, Claudio. Looking at all the various people. Andre Felinsky is here. We have Joseph and Didier, and waving to you all in the audience. Sam, I know some of you I've never met, but there are Adam, good to see you from Google Research. Great to have you along as well. And yeah, I wish we could all be together in person another time, but it's also kind of convenient to be able to do this online in this kind of format, and I'm really enjoying it as well. So thank you for the invitation to give a keynote or here, invited talk, I guess, is so I recently got the opportunity to write a history paper on FSharp for the HOPL for History of Programming Languages conference. And HOPL is only run every 10 years or so. So it's the sort of thing you put a lot of effort into trying to write the paper. And when I was asked to give an invited talk here at the workshop, I thought, well, I'd actually better talk about the things coming out of that paper because it's so relevant to the ML family of languages and the various research that's come out of that. There are plenty of much more technical talks I would have loved to have given. I was thinking just, in the last half hour, I was thinking I would love to just give a sort of deep dive on the inference procedures used in FSharp as they have evolved over time and why certain technical decisions were made, and also sort of, that would be the sort of more normal thing perhaps to be giving as a technical paper. So this talk is nothing like that. This is not a technical talk. It's a much more soft history talk in many ways. And so it's also kind of from a personal perspective, from one angle on the ML family of languages. There are other angles. I mean, Xavier gave a talk yesterday, which I didn't see, unfortunately, but on the last 25 years of OCaml that is highly related and intertwined. Then there are also talks on the history of standard ML and also history of Haskell, and also there are other relevant talks from across this spectrum. I think all the HOPL talks from this iteration of HOPL are available, and the papers are also available. They're all recorded and all available. Just look them up on Google. Okay, so it's a meta talk about a meta language, maybe even meta talk about a meta paper of a meta language. And it's loosely based on the HOPL 4 paper, and it kind of, in the way the paper I wrote was kind of constructed. It kind of takes an arc from the 1970s through to today, And mentally, now that very conveniently kind of fits into my lifetime. So there are always reasons for kind of choosing these kind of things. The 1970s are real to me. I was alive then, and the 1960s are in the far distant past. And so, yeah, starting around the 1974 is a very convenient thing for me. And I kind of think of it as starting from three guys get together. They are all guys, Milner, New, and Morris, Lockwood Morris, and Malcolm New, and Robin Milner, and start making a programming language. And here we are today, after this amount of time. Now, history is always written extremely selectively and with a purpose, with choosing various narratives for particular reasons. There were reasons why I did that in the FSharp.org paper. It's nice to be kind of just explicit about that. And I think I've covered the narratives. They may be narratives I've kind of forgotten to do. One is these things are a personal journey. You stick with these technologies. You get involved in these technologies for, well, whatever reason. Accident is the main part of it. I was at a university in Australia, and I had a supervisor called Malcolm Newey, who was one of the people who was one of the founders, first three people to create the ML family, the very first version of ML. And so I wouldn't be involved in that probably if I hadn't had that kind of personal interaction. And I think we all of us who've kind of been involved with this would have a similar kind of aspects to our kind of stories. But there's also a need for communities, highly technical communities, to have their own origin mythology, their own journey, their own perspective on time about where a language has come from, or what is it for, what's its kind of journey into the future. And so when one is writing a kind of history, one also has an eye on the fact that it's a history serves a purpose to motivate us about the future. Another theme that kind of comes out in the paper is that even in programming languages, things don't just happen. It's not just a technical or mathematical discipline. Even mathematics is things don't just happen. Things in some sense happen to people, to communities, and they act and they react and they change or reject or other things in kind of very human kind of ways. And there can be some element of creation in that. There can be rejection. There can be a sort of denial, a stubbornness, cooperation, subversion. There can be a lot of opportunism in some kind of aspects. And these things are certainly real in the way kind of technical developments happen even in our kind of field. And perhaps we're not necessarily that explicit about that, but it's certainly, when you look back over time, you can see these things kind of coming out. So another theme, a narrative, is this question, sort of, and this recurring narrative. What happens when computing traditions with very strong belief systems, and by that I'm meaning things like the functional programming community, those who with belief in mathematics and theory, for example, collide with other traditions, sort of more the system, I'll get to this a bit more later, but when you're at a place like Microsoft Research, you're very aware that there are very different traditions kind of coming into the same space. For instance, the systems tradition, where in a sense, the system that you're creating, the machine, these days, say maybe a cloud data center, that is the object of focus, and its performance and its systems characteristics are the kind of the center of the belief system of the people who are involved in that part of the industry. And there's quite a collision that happens when people who turn up who say, hey, I want soundness. I want things to be formally correct or something. These kind of traditions collide, and that can happen in industry, and it can happen in academia, it can happen just on the web these days as people are having a conversation. And I think perhaps in educating people in computing, we could be a bit more explicit about the different themes and the different traditions, because our students, I'm not an actual university lecturer, but when I think of the sort of things that maybe I would have liked to have been taught, is like there are very different perspectives on computing all coming into the same kind of spaces today. Another theme is, it's a similar thing about what's the interplay between academic research and industry concerns in computing history, and how it plays out in programming languages. And FSharp is just an example of that. There are many other examples of that coming out both in this talk and more broadly. Now, more closely to home in the history of the ML family languages, there are actually a lot of, when you look back in the history of the ML family of languages, there's actually a lot of contradictions built in right from the very start of the history of ML as a thing, as an idea, as an effort. There's a question of how one resolves and sort of makes progress from contradictions, sort of the dialectic that kind of happens in that. And I just want to draw out some of those things and how they played out in FSharp from my experience. And perhaps most beautifully, I think, or the most important thing for me, and I talked about this right from the start of the paper, is there are these remarkable things that have sort of held true in programming language design, or in what stands the test of time, what is the golden thread, and it's really quite remarkable to me that the core experience of programming in say Elm, or programming in OCaml, or programming in FSharp is actually in some ways very similar to what was being envisaged by the people who founded the first, who created the first thing we call ML. And when you consider how much change there has been in the computing industry over that time, it's really kind of remarkable a thing. And it's always a thing I come back to is, what's that core experience we're trying to deliver and support and make practical. Okay, so talking about contradictions at the heart of the ML family of languages, we're here at the ML workshop, and a lot of the papers, of course, about theory and about soundness, and that's a huge part of the history of the ML family of languages, applying logical techniques, formal techniques into the programming language design kind of space. But that's not how ML started. It may have been started by extremely theoretically minded people, but this paper is actually, there's a lot, which is a short note written by Robin Milner in 1982, looking back to the start of ML around 1974. And it's this thing that ML was for a more or less specific task. That is, ML was created for a purpose. ML was right from the start a practical language for getting stuff done. And there's quite a few comments all the way through this that kind of capture that. For instance, the section on lazy evaluation, it says, yeah, we decided this for no other reason than our inability to see the consequences of lazy evaluation for debugging. Okay, there's right at the start is utterly pragmatic concerns built into the heart of the ML, the very first version of ML. And he says, remember, we wanted a language which we could use rather than research into. Their initial concern was not to create a site for research at all. Okay. Their initial concern was to support their own productivity, their own programming. And they made various decisions, various compromises through that process. And we'll talk about a couple of, we'll get back to these a little bit later on, but you can see that right from the very start, these questions of purity versus practicality, logic versus pragmatism, they come to the fore, and they're quite willing to say practicality and pragmatism trump purity and logic. And that is there at the start. Now, there is this incredible kind of thing that happens at the start of ML, and one of the reasons I think that the thing about ML is it kind of serves to unify a set of interests during the 1970s and early 1980s of people who loved purity and loved logic, loved kind of formalism, loved well-constructed ideas, mathematically formulatable ideas, And it kind of served to unify them into a tribe of people, and that tribe creates things like Standard ML. It creates things like Edinburgh ML. It probably gets a lot of research grants for various kind of activities during the 1980s. It also allows a group of people to come together to say to the American research funders, hey, we've got this thing which is, we believe is beautiful. Here's a collection of researchers who will all agree with each other that this is worth doing, and then Standard ML gets created and so on. But one of the reasons why it's able to unify is because it's this coincidence of pragmatism and purity and logic. It's these two things kind of come together into a quite sort of, some people say it's a kind of local maximum, or a kind of just a point with a particular utility, and that's enough to kind of draw a whole crowd of people together. Now, if we roll forward to the 1997, the agenda wasn't actually that successful during the late 80s and early 90s, and we'll get into more about why. But in 1997, the various people involved in functional programming right across the spectrum began to be honest about where they were at. And that is that relatively speaking, no one was using their languages, and they start to be honest about why. And I had been one of the people using these languages during the 1990s, and as many of the people at this workshop, us older people here, and I was part of the tribe of people who were using these languages, but and I was experiencing them as being extremely productive. When I was using OCaml in the 1996, 97, when I was using Moscow ML around this time, they're just immensely productive systems. And I couldn't, as an individual researcher doing a PhD and other work, I couldn't imagine not programming in this kind of system. It's just quite unbelievable how low productivity these solutions like C++ or other things that people were using actually kind of were. So it was always a bit of a shock that no one was using these languages, relatively speaking. And if you want to go back in time and take a good look at this paper about Phil's sort of impressions as to why that was true, it had a huge influence on the development of FSharp, and it's worth going back for any researcher, any PL researcher who aspires to make something that gets widely used. It's worth going back and taking a read of this paper and having a good long think about what it actually means to make something usable by a broad enough range of people in practice. I do love that paper. Okay, so but things have changed. Just to say, we roll forward to today, and certainly typed functional techniques are used absolutely everywhere. There's, in some sense, ML owns the world in a sense, in that all these languages are trying to reach something that we kind of, this combination of types and generics and immutable data being much more prominent, and transformation, the programming centering on transformations of immutable data. These map, filter, reduce up there, real Python in the top right hand corner. This stuff is absolutely everywhere, totally normal part of the programming language spectrum today. So we have won in a very real sense of that. Also, strongly typed languages everywhere. Just putting a few of them up. Strongly typed functional programming languages. Whether you call TypeScript a strongly typed functional programming language or not, I don't mind. Certainly, JavaScript is a functional language in many ways, and TypeScript is a sort of strongest typed version of that. Also, Reason. We've also got the FSharps and OCamls and Swift and so on. So this is absolutely these languages are immensely practical, completely different space to where we were in 1997. So if we roll back to the 1980s and 1990s, let's just unwrap a little bit about what happened in the 80s and 90s, and who were these people, who were the functional programming tribe. And I've just shown some of the history. We've got Robert Milner, people like Larry Paulson developing Isabelle. It's strongly intertwined with the history of these theorem proving systems right from the start of LCF with Robert Milner. So then there's these semi-commercial implementations of things like standard ML that then get used in systems like Isabelle. And even today we've seen several talks interacting about the interaction between Coq and OCaml. And so there are also other pragmatic languages like Clean, and of course the development of the Glasgow Haskell compiler, less intertwined, kind of managed to separate off away from the theorem proving kind of world, and took in a role more on the kind of parallel programming role initially. But this was the kind of the world as it was, the relatively small world of strongly typed functional programming. And then something happens in 1986 to 1998. And this thing, which I've just used this stock graphic of a tsunami, which is not real, just computer generated, but it is this object-oriented tidal wave hits the world around in 1986 to 1998. Depending on when you start this kind of process, it was sort of exponential kind of thing, really. You can kind of start in 1986, 87 with this first OOPSLA conference and this sort of small talk, and also then Objective-C, which is not a language we talk about much in academia, but it had a huge impact across Silicon Valley in Apple's kind of rise to prominence. And then in Microsoft's academia, and then it comes along. So the thing is, what happens when you get hit by a tidal wave? Okay, and I think it's generally true that the functional programming tribe and the researchers who at the time who had seen their languages as being the future at that point during the late 80s and early 90s, they kind of knew their ideas were good enough to be the future of where programming languages headed. But they get hit by this thing, which completely wipes them out in many ways. And there are various reactions to what you do when you get hit by a tidal wave. So one reaction is just to give up. Okay, you actually stop believing, in some sense, in functional programming. There are plenty of people, for instance, who maybe stop believing in formal verification. They do a PhD in formal verification, and later on they decide maybe that doesn't work. So you just find something else to do and something else to believe in, and that's a perfectly reasonable kind of approach. Just because you start working in an area doesn't mean you have to kind of. It's only technical work after all. You don't have to believe in it forever. So another approach is to kind of reject, and this can be a very, very good approach sometimes, retreating to the fort, focusing on foundations, focusing, for instance, on pure and functional, focusing on various calculi. You might go and invent some new calculi, and in a way, Robert Milner does that. He doesn't actually continue to push ML that hard, in a way. He kind of, during the late 90s. He kind of says, actually, we're going to do the pi calculus. We're going to look at some really, communicating mobile systems. We're going to look at foundations for those. You might go back and create theories and logics of objects. Yes, you might. So there were many people who also, you can kind of look at Haskell itself as kind of a retreat to the fort and focus on sort of pure and functional, the Agdas of the world, and many other systems continue to push along this kind of line, and that is totally fine. There's a lot of amazing research has been done, and it allows people to be quite self-defining and not just to focus along certain dimensions of work. So another approach is to say, hey, I'm not that interested in functional programming anyway. Or, there's this very pure thing, which is functional in theory, and I love that. And I'm going to let there be a pure world, and I'm going to let there be a dirty world. There's going to be a world of God and a world of the devil, in a way. And the world of the pure world is where we prove things. And the ugly world is what we prove things about. Okay, we might be verifying C++ code or device drivers, for example. So we're going to accept that the world is constructed in really horrible and bug-ridden kind of ways, full of null pointer errors or whatever else. And we're going to spend our time using theory and functional programming to actually verify this stuff. That's obviously got a long history because of the association with functional programming with these theorem-proving systems. And I've just got some examples of how this plays out with people I personally knew. There are many, many examples across the PL landscape of taking this kind of approach. Another approach is this one where you say, oh yeah, right, it's great. I love Java. I don't like Java. But I like the JVM. Okay, I like the idea of there being this standard industry standard virtual machine. That's something I can get my head around. Let's get my favorite language and go and run it on those object VMs, usually with a lot of skepticism about the nature of those object VMs. Okay, so you're just using them as a kind of runtime target. Again, kind of saying we have this pure world, which is our language, and we have those object VMs as well. It's a means to an end to get stuff to happen. So some examples, Claudio, I saw in the audience, worked on the SML.NET compiler, which is very much in this mind. We also thought, so we got involved in doing quite a lot of this work at Microsoft Research through something called Project 7, which is talked about in the paper a bit more. There are many, many examples of this. I've called out MLJ as an early example in the 96, 97 kind of time frame, to take standard ML and get it running on the Java bytecode. It seemed crazy at the time in a way. And that was in the days when the Java was all about delivering stuff into the browser, which obviously got de-emphasized later on. Yeah, and so the idea of bringing this on more pure, cleaner languages, you can see the attraction of, so if we're going to write applets, we may as well write them in something like standard ML. Okay, another approach is kind of the rational deconstruction of pulling things apart bit by bit, and to say, and I'll get onto this more later because it's strongly used in FSharp, is to try and rationally deconstruct functional and object programming and say, well, what is functional programming anyway? Is it just lambdas, okay? Or is it type classes? Or is it functors? Or is it, what are the primitive calculi we're kind of using, but also what are the actual language constructs? Does it include pattern matching or not? Does it include discriminated unions, etc.? And also to rationally deconstruct object-oriented programming. And so we've got this thing called object-oriented, this tidal wave that's hit us. But what are they trying to do? Oh, they're trying to do existentials. So they're trying to do sort of nominal typing or structural typing, and we can maybe do that better if we just pull it apart in the right kind of ways. And part of that agenda is to try and seek a synthesis between two worlds. Instead of keeping the worlds separate, like I was saying, you might try and let your worlds merge. And one approach is to make functional languages more object-oriented. And there are many examples of that. Dylan is a bit of an example, not strongly typed. OCaml and Haskell or FSharp, but there's actually many more. But they're still starting with what we would recognize as a functional programming, strongly typed functional programming language, and then seeking to add sort of objects to that. The other approach is to go for the object-oriented languages and to kind of integrate more functional language techniques. And so one very important part of the history is a thing called Pizza, just done by Odersky and Wadler in 97. So you can see the dates. Yeah, the object-oriented tidal wave hits around 1993. And then it takes around 4 years for people to kind of really digest that and kind of synthesize that and then come up with a response to that. Okay, they get over their denial phases and they kind of say, okay, right, we'll think about what we're going to kind of do. And they add things like generics, but it's interesting, they're still using the language of the functional programming community, parametric polymorphism, but what they actually mean is generics, and then you see they add these other things, algebraic data types. Again, they don't even say unions, they just say algebraic data types, etc. Okay, they seek a synthesis. Okay, lots of other examples of that through the history. Scala, it derives from its efforts, from this kind of effort. Absolutely. You can see it in Java, C# and C++ more recently. Things like C omega are also part of the kind of history that was fairly close to from my perspective. Okay. Meanwhile, so that's the world of these object-oriented tidal wave and the academic, this small tribe of strongly typed functional programming kind of people. Meanwhile, in that bit of history, we had, there was Microsoft and there was Netscape, and then Java came along, and then there were lots of lawsuits. And so Microsoft itself, one of the monopoly companies in the industry, is getting wiped out or hit very hard by this object-oriented tidal wave. It also, these things don't just play out amongst academic communities, but actually Microsoft was also kind of having to deal with this in its own way, and it did its, and part of its resolution of that thing was to create Microsoft.net. And it also created Microsoft Research, and Microsoft heads to Cambridge. So let's talk about that. So Microsoft Research is founded in Cambridge, and one way to look at it is all the tribes of computer science. I mean, 500 or 800 people are employed by Microsoft, and they're top-level computer scientists and entry-level people like me coming out of university and so on. And in a way, I look at this as kind of the worlds of Robin Milner, that tribe, and the industry concerns of Bill Gates collide full on. There are many other collisions are happening as well, but this is one particular collision, and it coincides with the start of the .NET effort at Microsoft. And so what do we do? Well, we play various versions of that game, those responses that I described before. One of the things we did is to put generics, parametric polymorphism, right into the heart of the strongly typed intermediary language, which is the .NET IL. And in a way, I think this, from my perspective, we were kind of breaking through the nominal class-based this dominant ideology that everything had to be an object, and there was no other way of looking at how to model how to model information except inheritance, class-based inheritance, all completely nominal. And so to bring in parametric polymorphism into the core of the system and get it into C#, to get it into even Visual Basic has this, and provides a really strong foundation at the core. And at the time we said it puts .NET 20 years ahead. And I stand by that, because Go, for instance, is still absolutely struggling with generics today, what to do with generics. And in the end, the system we have in .NET and Java still don't have it in the JVM, and it really makes a difference from many usability perspectives, performance perspectives. This was the sort of thing we wrote at the time. We were kind of saying, hey, there was this thing called Com+. Well, it doesn't matter what that was. One of the early names. Okay, sorry, just checking. My connection may be interrupted. We'll see. And we said, get serious about language innovation.
We can't see screen sharing anymore, I'm afraid.
Let me re-share my screen then. Got it. Thank you for letting me know. Are we back on?
Now.
Okay, great.
Yeah.
Right, so we are here getting serious about language innovation, and we're kind of pushing on the industry buttons that they were only going to be able to compete with C# and to make it a kind of strongly technically compelling language if they actually innovated with it and got ahead of the game. So we were kind of pushing Microsoft's buttons that it hadn't done enough innovation in the past, that it was time to actually do this properly. So we landed .NET generics, but then from our perspective, when I say our, I mean the joint researchers at Microsoft Research in Cambridge, it still wasn't what we wanted. it was still too verbose. It was kind of unusable, in some sense untrustworthy, if you consider just null pointers absolutely everywhere. And there's still this open kind of question about, well, what to do about this. I mean, sample after sample just kept showing this. Just we started doing early prototypes of I did of things like FSharp, and you just get these code size reductions of like for like code, and the C# code being full of null checking and the like, and it's just not where we wanted programming to be. So a later example of that I like to use, it was written up by a guy called Simon Cousins. It's from an application in the UK energy industry, just to show we're not making this stuff up. I'm rolling forward a few years here. And he wrote a blog post called "Does the Language You Use Make a Difference?" And he did a couple of versions of that. I think you can, that particular website link at the bottom is no longer available, but if you go to the fsharp.org history paper, you can find the links to the archive versions of these blog posts. And in this kind of world, the C#, people using C# 2.0, 3.0, compared to people using FSharp for pretty much the same kind of problem. And you can just see the kind of line count differences here, 56,000 lines of braces or 3,000 null checks and so on. So at the time, I was using a lot of OCaml. It's by far the best practical language at the time. And FSharp 1 was kind of born from this obsessive, perhaps overly obsessive, I'm not sure, desire to make sure that I personally would have a language I wanted to use, and that sort of strongly typed functional programming in the OCaml or the Camel Lite tradition. Camel Lite was always my mental starting point, not the O in OCaml, even though I'd actually been using OCaml. And to make sure that was a viable option into the 21st century. Okay, so this was the sort of slides we presented I presented around Microsoft, binding us, just kind of saying, yeah, it's nice and simple. For that to do all these different things, and you get nice type inference with a sort of just as safe as C#, actually safer than C#, with the succinctness of a scripting language. Mentally, I was thinking of there being this beautiful racing car called OCaml, French and sleek and kind of wonderfully constructed, and saying, yeah, let's keep as many of those qualities as we can, but we're going to run it with an industrial grade truck engine called .NET. Now, actually, that's not my mental model these days, just to be clear. I'm just trying to capture how I was thinking at the time. I actually think the .NET runtime is a superb basis for a functional programming language. Certainly a great basis for FSharp. I don't have any complaints, almost no complaints about the .NET runtime. It just gives us so many wonderful practical things that we need. But just to say, that also captures a lot of my respect for OCaml as I was using it in around 2003, 2004. Okay, so the approach we took was starting with core OCaml. So try and stay true to the functional programming principles and try and make it always possible to whatever else we added for whatever purpose, you could always come back to core OCaml, which was the sort of core productivity experience of ML as it had been developed in the 1970s. So just to make sure that golden thread stays true for the using FSharp. So we used, we had a fair amount of camel code that we could use to kind of pin down the core implementation. And we say, we want this stuff to always continue to run because it's a great way to program. And that we know for sure. And whatever else we do on top, we make sure that core productivity experience is always maintained. And then we interoperate, we reuse this VM and ecosystem. This actually means that FSharp kind of has this exosystem in a way, that it kind of lives inside the .NET ecosystem, or at least initially does, and now also in the JavaScript ecosystem. And so that is interoperability is a major concern for the language right from the word go. Okay, we deconstruct object orientation when we find a synthesis. We learn from C#, and in the sense that we say we're going to put in IDE tooling, developer tooling, right from the start, going to have a REPL from the start, but above all, the language is going to pretty much assume that you've got a richly tooled development environment, which is now kind of standard. And we deliver it, we apply it in industry. Microsoft and Microsoft Research will act as kind of a long-term home for the thing. And then we iterate and we improve. And that's been pretty much the approach all the way through. So if you kind of think, well, what does that mean in practice? If our starting point is core OCaml, or core Camel Lite, or the core of the ML programming language, then what directions kind of can we go? We don't automatically assume anything. We're not starting with standard ML, like say SML.NET started with. We're kind of just reducing down to this expression-oriented core that we know is productive. And then we kind of look in various directions. And now there are, in the history of the ML languages, there's been a tendency to go in some directions more than others, okay? So for instance, there's been, in the 1980s, there was a tendency to go towards formalization in creating the formal definition of standard ML. So, but there are 6 or 7 or 8 or 9 different dimensions to programming languages in a way, and you can kind of move along those dimensions or explore in different dimensions. And so I've tried to brought out 6 of them here. So, and what do we do in these different dimensions? So if we just think about, parameterization, well, of course we have functional abstraction and parameterization for the Lambda, right? But do we kind of venture into this functors, parameterized large components? And no, we don't do that. And I've got lots of answers written up on the web about why functors aren't in scope for FSharp, or why they don't seem to find the utility that they might find, or also some skepticism about their sort of utility, even if they're theoretical, even if the theoretical foundations I fully kind of appreciate and love. So that's kind of one space. In the kind of, we obviously start with this core immutable data by default, algebraic data, but we actually do embrace kind of functional objects as a way to kind of get enough encapsulation. And we're also getting some interoperability from this kind of space. We go in the direction of nominal objects, some of it driven by interoperability concerns, some of it by outright just access. So a great way to get existentials in the language. But we don't go into the kind of structural objects kind of space. We've got a little bit more like that in recent versions, but initially we through a thing called anonymous records, but we don't do that by default. On soundness, okay, initial focus. We want initialization soundness. The let keyword is trustworthy, right? That there are no nulls. You know that if it says let x equals y plus 1, then x has a value everywhere in its scope and it's well initialized. There's this kind of, in the functional tradition, there's this kind of, along this dimension, you get sort of more and more extreme, which is sort of soundness is supreme. Sort of the idea that if there's one unsoundness in your system, then the whole world kind of collapses. And from a logical perspective, that's true, but it's not true in the pragmatics of programming. And then there's an even more extreme, which is that languages sort of don't exist unless they have a formal specification. They have no reality, sort of mathematical reality, or they're just nonsense. And that's not the approach we take in FSharp. It's a kind of fine, kind of extreme position, and I appreciate why people have that, but it's not where we were. So let's put that in that kind of grayish kind of color. On types and type inference, we start with types. What are types for? And this goes to the heart of things like .NET and Java. Types are for modeling. For domain modeling, types are for performance, types are for correctness, types are for interoperability. So that thing that types become for interoperability between languages is the fact that we incorporate that into FSharp means a lot of other things change about types. We have to kind of accept what we get for interoperability with regard to our view of types, but it means maybe we can't use types for the purposes that other people might use them. We want to keep Hindley-Milner, and this is a major design decision in FSharp, because we want that core ML experience, which involved Hindley-Milner type inference. We absolutely kind of want to keep that. And Scala doesn't keep that. In fact, almost no other languages. Elm does, but very few other pragmatic languages in the attempt to combine with object programming kind of keep Hindley-Milner. And we modify it for objects. When you're not using objects, you still get Hindley-Milner, but when you do use objects, things kind of change a little bit. You need more type annotations. We also add things like types for fast generic in math, but we don't go towards type classes and that kind of parameterization and type level computations. Types for logic and proof, that's out of scope for FSharp, so we kind of limit our exploration along that dimension. Now, there's another dimension I'll get back to more, computational modalities, and that's things like list comprehensions, monadic notation in a language, or more generally, you might have queries, async, monads, monoids, applicatives, and compositional computation notation. That is an area we do push quite a long way on in FSharp, and a lot of that is covered in the history paper as a section on the kind of history of that. I'll get to that a bit more as well. So on interop, we did take a radical design decision that FSharp types are .NET types are FSharp types, and especially for the early versions, we've modified that a bit to have a richer system in FSharp which reduces to .NET types. And we also took this view on type providers and sort of metaprogramming for which I'll just mention a bit later on as well. Okay, so you take the parts off here in gray, and that's sort of more or less the exploration of where FSharp kind of lands in each of these dimensions. Okay, so along the way, there are reasons why we made some of those decisions, and that involves facing some of these kind of contradictions that are built into the strongly typed functional programming tribe. And I gave that these sort of contradictions: purity, practicality, logic, pragmatism. And this idea that as you have a contradictions between an idea and its kind of opposite, or it's what seems to be its opposite, you kind of do this Hegelian dialectic thing and say, well, let's try and find a synthesis. Let's try and find a way forward out of this set of contradictions. And I like this approach. It's obviously, philosophically a very strong approach in the 1800s. And I think it's an important sort of the foundation of how we do research in this kind of area. So one of the contradictions was to do with objects. And if you go back to that paper, even in 1982, Robin Milner is completely aware that they don't have notions of encapsulation or abstract types really built into these versions of ML very well. That applies to both pattern matching and also just objects in general. And in my point of view is that practical type languages need to have cheap and effective type declarations for encapsulation, and they may as well be called objects. Previous MLs had awkward variants of that, abs type, and then the kind of module and functor system is pretty awkward for doing. It's not what you call sort of cheap and cheerful for that. So we do put in object programming into FSharp. It's sort of modified Hindley-Milner, type-directed name resolution, nominal, subtype, friendly inference. It tries to be focused on delegation as much as possible and tries to be friendly with regards to expression-oriented programming. This is what object programming kind of looks like in FSharp, just in case you've never seen it. You have the type, you're still defining types, and you're still using let in the middle. You can have all the let of functions and whatever else you do. And then you publish an interface, you export an interface to the object with properties and methods along the way. So that's fine. So you get this ergonomic simplicity of encapsulation. Works very well with type inference all the way through. And things are still immutable by default. So you're not buying into the sort of the mutable state view of objects. So along the way, we kind of also deconstruct object-oriented programming. And this is kind of a list of all the sort of things that kind of are in OO as you get it in the world of .NET and Java. Or it's .NET, but it's more or less the same for Java. And so you pull it apart into all the different pieces and you kind of think, what do we want? What don't we want? And you more or less, you scratch your head for a very long time. And you have a lot of arguments with people. And then you kind of, those things can be broken down into different areas. So some are just about making a better language for writing and designing software components. And that's a major focus for .NET. Some are about making it a better language for implementing code. Some are about just participating in the interop standard, and some just are not needed at all. So more or less, we break it down into these, which is you embrace these ones in green. You use these blue ones kind of are in the language, but you try to use various techniques. Only use them where necessary, use them where tastefully, just sparingly. And then the red ones are like, yeah, they're in the language, but don't do them, right? You know, these are going down the rabbit hole. You can do these things by various ways, but you kind of strongly restrict that both culturally and kind of technically. And there's some things that are just completely not supported, like, you know, wildcard types or aspect-oriented programming. Okay. So yeah, so you love these. We encourage people to love a section of object programming, to tolerate some other aspects of it, avoid some, and then completely forget about a chunk of the rest. So part of that is that I really don't like the term object orientation. I actually want the industry to stop using the word object orientation and just start using the word object programming. And that is because object programming is good. You know, there's lots that's positive about it. Succinct coding, convenience, ergonomics, good naming, encapsulation, small composable abstractions, expression-oriented object implementations, delegation, closure, and above all, you're making relatively simple things out of potentially complex objects. You can wrap up a bunch of objects, encapsulate, and make something fairly simple. Whereas object orientation is just stifling, right? Objects is a single dominant stifling paradigm. It's absolutely pointless waste of time on hierarchical classification, animal, cat, dog, abstract jelly bean, factory. And you get these large cumbersome abstractions with many holes and many failure points based on declarations. And above all, you make complex things out of complex foundations. If you're using hierarchies and implementation inheritance, you can only make things more complex by inheriting from something. And so the FSharp approach is nowadays to embrace object programming and make it fit with that core ML programming, but absolutely not to embrace full object orientation, except maybe if you're in a project that is already using that technique. But that's where we land. Okay, and in a way, we're trying to get back to this sweet spot of programming. I do like this slide. It's quite challenging to people, which is that the sweet spot of programming is functions and data, or which from our perspective is functions and data plus just enough types to support the action of programming productively. And in this slide, it's kind of down the left is code complexity increasing. And you start with this kind of code of functions and data, and then you start going crazy about object-oriented programming. You're using abstractions, interfaces. I might need to change something later, and design patterns and so on. And then you come back to functions and data after you get enough experience not to do most of that stuff. And then you do the same thing all over again when you come along the functional kind of dimensions of applicatives or category theory and purity for absolutely everything, and returning exceptions as data for absolutely everything or something like that. And then after a while, you come back and you land at the place of sort of functions and data. And that is always the kind of sweet spot that we're trying to choose. And we're just kind of subjugating objects into that notion of data. Objects are a perfectly fine notion of data for many purposes. And we can write functions, or we can write data, and some of that data is objects, and we have enough types to look after things. So another contradiction built into the ML family of programming languages came in when pattern matching was added. And there's this big problem built into pattern matching, which was known fairly much straight away, which is that pattern matching over concrete representations is in practice a software engineering catastrophe. And it was a contradiction in all functional languages. And I think FSharp was one of the first to really address this problem in 2006. Scala was addressing it about the same time, and Haskell eventually does it with view patterns. But Robert Milner knew this, right? He says, if you read the thing at the top right, he says, ML does not adopt the clausal form of function definition, which is found convenient by Hope and Prolog. How can we possibly do this when we want this to not just imply primitive constructors, but the constructors of user-defined abstract types, that is objects in some sense, or that is abstraction. And so and then he says, well, you know, we don't. This was the versions of ML before they added pattern matching, and he knew it was wrong to, in some sense, it was wrong to add it without addressing this kind of problem. But they added it in anyway, and FSharp has a way of addressing it, and it, in my eyes, it's a way of resolving that contradiction. There's another contradiction built into the entire world of functional languages, which is this idea that Lambda is everything, Lambda the ultimate. You know, we all worship the Lambda. I still do. We all do. And but Lambda's not the ultimate, right? Because we use these computational modalities to extremely good effect all the time. And you might say, well, that's just Lambda combining with monads or something. But we, if you need to digest this into your language design to kind of say, actually, we're going to embrace computational modalities, whether that's monads or applicatives or list comprehensions or queries or whatever else, and support those right from the start. And that might be tasks, various takes on DSLs and so on. And if you take these 5 different C# features, for example, C# going full on in embracing various computational modalities. It has query expressions. It has collection initialization. It has these async methods. It has iterator methods and async iterator methods and so on. In FSharp, they all become one kind of construct. It's a fairly sophisticated construct. It has to be to encapsulate all of these, but it's still just one thing with one set of rules and fairly natural rules, which is where you put a modality of some kind around some code, and then that, and so that's some examples. You might get seek plus a yield effect. You might get query plus a yield effect, or a list, or an async sequence, or a coroutine. Okay, so just some examples. So where you previously had code like this in OCaml, which is you're in the modality of generating lists, okay, you would instead use the FSharp thing for list here, and you would you then just use for loops, right, and if statements for your filters. So you just got a generator, and yield bangers for yielding many things. And the code is really nice to debug. It's really nice to read, and it encaptures many. It's like list comprehensions on steroids in a really positive way. It's one of the most positive features of FSharp, I think. And you can have whole chunks of your program written in these modalities, and it's very easy to transform your code from one modality to another to make this an on-demand list. You just use seek around it instead of using the square brackets. Okay, so this thing about putting computational modalities into languages played out quite a lot during the sort of co-evolution of C# and F#, and there's influence from the outside. So you have things like Snowball and icon iterators coming into, via Microsoft Research, coming into C# in 2.0. Then F# kind of says, oh, yes, we can do that too. And we put in like async await and comprehensions and computation expressions and sequences. And that's influenced by a whole lot of work from the functional programming world and the theorem proving world as well. And then in the meantime, C# says, oh, yes, we can put in queries, and it does it via a completely different mechanism. And we, in F#, we just say, okay, we've got this one mechanism. Let's just make computation expressions, which is the unification of all of these things, support queries as well. And we also do asynchronous sequences. And then C# says, oh, look at what F# is doing. They're doing asynchronous programming. Isn't it nice? Doesn't it make parallel programming or concurrent programming really simple? And they put in async await, and it's influenced by other systems. And then async await actually are now escaped out of this world into the world of Python, C++, and Java. And so there's direct heritage from ML-Donkey or these various things in the functional world directly through F# to C# through to Python, C++, TypeScript, and others. And in the meantime, C# doesn't stand still. They kind of look at asynchronous sequences in F# and create asynchronous iterators. In the meantime, F# already has that, so we put in support for a slight modification to allow you to do applicatives in the same kind of way. So there's the history of how that develops. And it's actually a really sweet part of F#. I encourage people to take a look at that. There was also a contradiction between typed code. I just noticing my hour is coming up, so I'll be another 5 minutes or so. So between typed code and external data, and that leads to FSharp type providers, and it's about external interop, a metaprogramming system for external interop. Okay, so the more recent history of FSharp, there's a lot I could say. I've kind of tried to focus on those origins. I share my screen again. Okay. Okay, so the more recent history of FSharp. So 2010, FSharp kind of lands in a tough part of the industry, I would say. The kind of enterprise programming that companies like Microsoft support with their programming languages can be extremely conservative. There can be some very progressive parts of it, and we got lots of people started using FSharp. But there are also, extremely conservative enterprises which where there literally nobody knew anybody who had ever done anything in any functional programming language. Certainly not a strongly typed language like OCaml. And so was in retrospect quite a tough part of the industry to land in. And the other thing is it was also Windows dominated, and of course Windows had to. It's not in a sense until 2014, 2016 that I think FSharp actually becomes fully real and normal as a language, because we're finally cross-platform. We finally have a great Linux story, and this corresponds to the industry move to the cloud, where using Linux becomes totally normal. And we're fully open source, and just so in some sense, FSharp properly begins there, because we're finally a normal language with a normal cross-platform open source existence. And that's been a wonderful transition. Okay, and then we've done a whole lot of versions of FSharp, which I won't get on. So today, what is FSharp today? Its core position is as a typed functional programming language for .NET and JavaScript. Trying to capture that simplicity of experience of that was there in the first versions of ML, and is sort of staying true all the way through. It gets delivered wherever C# does. It's delivered in what's called the .NET SDK, and it's really good performance characteristics. And it's so sweet spots are for web client, for mobile, for server, for cloud, and it's also got some good technologies for deep learning. Okay, I'll skip the last part on that. Just some slides about if you want to use it and get going, you just type .NET new -lang FSharp. We do .NET build. The tools are everywhere. If you want to get going for the web backend, you just get some templates and create your first app. If you want to get going with the front end, it's sort of similar thing. Get some templates and create your first JavaScript application with FSharp. And if you want to do the full stack, there's this wonderful system called Safe. You get some templates, you start, and you get going, and you can deploy through to whichever cloud you wish. One lovely vignette from the paper is about this building, which is the Louvre Museum in Abu Dhabi. And the code that computer generated the parts for the roof, written by an Austrian engineering company, is actually a 3,000-line FSharp script. And I always like to look down on the satellite photos of this building and imagine there are lambdas encoded in the roof parts of this iconic museum. And I'm looking forward to the day I can actually go and visit this museum and remember that strongly typed functional programming is part of physically creating it. And you can read about that in the history paper. The influence of FSharp, we lived right next door to the C# team, and it led to many direct influences both ways through the various people I've mentioned here. Some of them went to work onto TypeScript as well. And if you look at the features of C# in this big long list, then the ones I've highlighted are all pretty much strongly influenced by FSharp. You can see down the bottom left, tuples and deconstruction, pattern matching, local functions. These things are ML, right? They're strongly typed expression-based programming. There's one down here, just hidden down the bottom, nullable reference types. So nullable is on the decline in the C# world, or nulls. And from one perspective, they finally corrected the billion-dollar mistake. Surely the real cost of that mistake is like up 100 billion or something when you consider the lost productivity in the software tech industry because of nulls. And so we are really making the industry move ahead one way or another. F# has had a bunch of other influences. I've mentioned some of them along the way. Okay, so just to recap, the programming world has corrected the dominance of the 1990s. The object-oriented tidal wave has come and gone, and we're in a much happier place now. A whole lot of techniques have occupied their place as practical core techniques in nearly all programming languages. The idea that no one uses functional programming is completely, permanently consigned to history, and F#'s been part of that story all along. And for me, that golden thread of the idea of a language is to support the use of functions and data through just enough types and just enough verification or just enough whatever else is going on. But functions and data is with this sort of sweet spot. I think Milner, Newey, and Morris kind of saw that in 1974. It's what they needed for LCF, and it stayed true all the way through the history of ML. And thank you. And I'll be very happy to take some questions. Sorry to go over by 5 minutes.
Well, thanks, Dan, for a most exciting presentation that really did cover so many facets of like the design and history of F#. That's a very happy audience. You're being showered with emojis flying in every direction.
Thank you.
All right. There's plenty of things I want to ask, but I'll start with the audience. Sam has a first question.
Great.
Oh, no, I said Sam. Okay. If you were starting a similar exercise now, but targeting WASM, do you think you'd arrive at a language like F# or something different?
I personally wouldn't be targeting WASM because I wouldn't know what its interoperability exosystem is yet. If it's JavaScript, then I'll just still target JavaScript because would it be F# would be different if we targeted JavaScript originally, without a doubt. Since this absolutely affects the syntax all the way through, it would end up much closer to TypeScript, just without the incremental typing, probably. Let's take another version of that, which might be of interest to people, is what happens if you're targeting interoperability with Python as your core of your system. I think it's an open question, and it's exactly the kind of question I want people to engage with from this talk, is what would it mean to create a language which actually can utilize all the assets in the Python ecosystem. And Python is beginning to be more typed. It's beginning to be more buttoned down around the edges. So it's possible to do that. There is, in fact, an F# to Python compiler as part of the Fable effort. I don't know the full technical details, but yes, the choice of exosystem to locate in is absolutely crucial. And you can get too close to these systems as well, in that these systems change over time. They evolve, and .NET has evolved, and sometimes we've been a bit too close to .NET, and as it has improved and evolved, it's kind of, we've had to take the sharp corners with it along the way. So I don't know the technical details to that answer, but the answer is yes, we would arrive at something much like F# in that it would still include that core ML programming experience. So large chunks of F# would stay exactly the same from my perspective, but around the edges, there's a lot of difference.
All right. Next one. Gabriel has a question.
Yeah. So C# 4.0 introduced this dynamic type thing for sort of gradual typing. It's kind of it is possible to do this in F#. It is not actively used in practice really at all in F#. yeah, boy, when I hit C# code that uses that, I hate it. I hate it so much. I'm really, really furious when people use that as part of, unnecessarily use it as part of a DSL design.
Cool. Moving through the questions, this one already got an answer from Gabriel actually in the chat with a link to the reference documentation for computation expressions.
Yep.
Do you have anything to add?
Well, just to say they're absolutely user definable. If people are interested, you can type in my name or dsime and applicatives, for instance, if you're interested in how to do applicatives in FSharp and that particular kind of computational modality. But yeah, no, they're absolutely configurable in quite a number of interesting kind of ways.
Great. Next one, Matthew.
Okay, so what did .NET get right so that it worked well for FSharp? .NET was a relatively more static system than Java right from the word go. I think when Java becomes big in the industry in 94, 95, and the Microsoft engineers kind of are looking at Java and they kind of see this, what is effectively kind of a cut down type small talk kind of system and lots of virtual dispatch everywhere. And they say, actually, we want something, our experience in writing code tells us we need, and delivering production operating systems and applications means we need something much more static because, for instance, we need to patch these programs with security fixes or bug fixes, so we need a much more static world. So right from the start, .NET took a substantially more static approach, sort of culturally, than Java. And that goes through its library design. And they also took a very different approach, I think, a more cut down use of, say, object-oriented overloading. They kind of restrict down in a number of ways. And all of those things help FSharp as FSharp starts. Now, then, of course, we feed in generics into .NET, and that is absolutely the foundation from a performance perspective. And I talk about why that's the case. The fact that we use code expansion for based on type representations for generics means that we don't get any implicit boxing all the way through. More recently, the .NET, I don't know, the .NET garbage collector is very good. The .NET native code compilers are very good as long as they allow the possibility of JIT at runtime. The willingness, the .NET people have a willingness to put things like tuples into their core library fairly early on, which did help us. There are some things like debugging that the .NET virtual machine and profiling, the APIs the kind of foundational machinery for doing those things works extremely well, and we often actually have more capabilities than we actually exploit for FSharp today. And especially, I guess, from the garbage collector. The garbage collector is just great it seems to be great for functional workloads. And I actually think it's a bit of a myth of the functional world that somehow these .NET-like garbage collectors aren't good for the program. They're very, very good. So,
if I actually may interject for a related question, when you think about OCaml, when it targets its backend, the backend and the runtime system of OCaml are extraordinarily untyped, right? With a completely universal value representation and that completely uniform GC representation. And my understanding is that .NET, as you just said, is much more typed and much more structured. So how come you didn't get an impedance mismatch, seeing that you share so many traits with the original spirit of OCaml?
So there are some places we do get that impedance mismatch. One, for instance, is the fact that core camel included structural comparison and structural equality.
Yes.
And it's based on revealing that internal representation effectively.
Mm-hmm.
And we actually have that in FSharp, and we pay the cost for that very badly in technical features. When you really, there are ways you can constrain those features come with performance overheads that may not be expected for people. We do a lot of work in the compiler to reduce out those performance overheads, but boy, it's a lot of work, and you can still fall into holes here and there. So yeah, so but more besides that particular manifestation of that, actually, .NET's an interesting system in that the key thing is that .NET generics handles polymorphism with respect to all those varied representations. Okay. And that's the key. And it allows, for instance, our integer types aren't 31-bit integers like they were in Camel for a while, but they're 32-bit integers, and lots of positive things end to end about how the core ML implementation actually plays out in practice. Yep.
Yeah. Okay, so it was really the whole generics work that unlocked the ability to do FSharp.
Yeah.
Okay.
There are some technically adding GADTs is harder because we don't have that built in, and we don't have sort of notation of existentials in quite the way. Claudio is here. He's actually done papers on that back in the 2000s about how you can get most of that kind of effect. But when you're having the other thing is higher kind of types is not present in the design of FSharp. And that's because it's not present in the design of .NET. And also type classes is an interplay there. And there are also interoperability concerns here. Do we put in type classes into FSharp? Yeah, we could do that. And we have a kind of some type class-like mechanisms with regards to generic arithmetic. But if we do, and C# does that as well, then we're going to get a really bad interoperability problem because they're not going to do it the same way as us. So we have to really do it the same way. And so I'm okay with that, actually, because there are pros and cons to type classes anyway. Yeah. But that core question about representations and what mechanisms sort of deal with that, is it the runtime system or is it the language? And what are your representations of values? That's all playing out through those discussions.
I see.
Have we considered? Yep.
No, go ahead. I was just saying Sam had a question.
Yep. Considered adding support for effect handlers, as in multicore or Camel. So not really, because sort of effect handlers became more in vogue after most related parts of FSharp were already settled. So, I mean, I've considered it. Yeah, every time I see a talk on effect handlers, I'm impressed with the work and I kind of consider it. And computation expressions could interact very nicely with effect handlers as a sort of syntactic mechanism. I haven't. I mean, no. In terms of actually pushing that onto programmers, no. It always seems to be beyond what the programming world will consider palatable. The parts of the industry we're trying to address, it would seem to blow the complexity budget. I might be wrong in that. Someone else can prove me wrong, I guess.
Next question.
Okay, yeah. So this is so there's a question about you get exposed to nulls through using .NET objects, and in theory, .NET objects can be null. And that's absolutely the case. Now, the .NET libraries very rarely used null, and they almost never return null values. So this is not a serious problem in practice, okay, in using FSharp code, because of the design considerations of the .NET libraries. Now, you can get exposed to them through serialization, and that is an important area. So the other thing is that this business of C# getting null reference types means that every single .NET library coming through the system, in fact, they just announced that they have completed the process of annotating all the core .NET libraries, and it's a very large framework, with nullability annotation. So the first time in industry, a set of significant libraries which actually contain so much functionality, let's just point out, say, Unicode or globalization or whatever else, they're all coming annotated with null nullability annotations now. FSharp doesn't yet incorporate that information because, as I said, it's not much of a problem, and FSharp values are nullable, not nullable by default for FSharp defined types. So when I say the problem is solved, I kind of take a long-term point of view in the sense that we are on a path where the number of nulls in the industry, or that $100 billion mistake, is kind of going down. You know, the amount of future, the costs into the future of those kind of mistakes in industry. So we're on a path to seeing that change in the basis for programming in the industry, at least in our part of the industry. Oh, okay, yes. So I didn't mention that in the history of FSharp. So FSharp does have unit of measure types put in by Andrew Kennedy primarily at Microsoft Research. And yeah, they're really nice. And they are a sort of very additive to the system in that we make sure you never see these things unless you start to use them. And so it's a sort of feature that people either use or they don't. And there are some people in industry who use them a lot. And so I'd probably, at a guess, about 5% of FSharp users, 3 to 5%, would be using unit of measure types. Now, there's two variations on that. One is whether you're just using simple kind of tagging of types, but effectively it's kind of colors on types. Or are you actually using the algebraic properties of units of measure? So meters times kilograms equals kilograms times meters. I would say probably only like 0.5% of FSharp users would be using the algebraic properties of unit of measure types. But when they get used, they happily give talks about how important they are and how crucial, you know, for controlling complexity. There is a problem here, which is that numerically intensive computing has gone very much in the direction of tensors. And tensors these days don't even carry static dimension information about the number of dimensions, for example, let alone the size of the dimensions, let alone the unit types for the information carried in those dimensions. And in fact, those tensors are often carrying a complete grab bag mix, where the first 10 elements of a tensor are in one unit of measure, and then the others are in other units of measure. So there, in other words, as much as I really like the feature in FSharp, its utility is kind of reduced by the way numeric programming is done in practice in industry today, and I don't think anyone has a good solution for that. I know Adam Paskey, who's worked on PyTorch, is here, and he would be very aware of these problems as well, and how they play out. So yeah, no, there's a lot of unsolved problems in AI programming for the practical rollout of types in AI programming.
I think we finally reached the end of the question list. That was a lot of questions. This is great.
Okay, my pleasure.
I think we only have 7 minutes left of a break before the next session. So how about we all give everyone a breather before the next session restarts. Thanks again, Don, for this really great talk. It's been a pleasure listening to you, and I hope to see many more FSharp submissions at the ML workshop in the coming years.
Yeah, we will look forward to that, and thank you very much as well. If anybody's got any follow-up questions, I'll be looking at the chat, or send me a message on AirMeet, or just contact me privately. Okay, thanks very much.
All right, thanks. Bye-bye.